Okay, Houston, we've had a problem here.
This is Houston. Say again, please.
Houston, we've had a problem.
Houston, we don't have a problem. Today what we want to do is we're going to talk about something called projectile motion. So this is when an object gets shot out of a cannon, or a golfer swings at a ball, or a basketball shoots a basket. The official definition of projectile motion, so copy this down, is an object moving in two dimensions, key two dimensions, but only accelerating in one direction. So if you think of a golfer, so let's say we've got a golfer at the tee box, and he has a golfing ball, like the golfing ball pink, and then he takes his club, he swings it back and he swings it forward, but what happens is the ball is shot out at an angle, two dimensions, both x and y, and it forms an arc when it comes to land. This is the land right here, right? So that's the definition of a projectile, right? You're going to know, for example, boom, the angle, we'll call that theta, of the launch, and then we can determine where it lands. So the math, this is used in a war, when a artillery shell is shot at a particular angle and you want to hit the target over there, a ship off the coast of the land, or et cetera, or whatever. And when we talk about this, the key thing to understand is that when we talk about what we know and don't know, we have two tables to work with. We're going to have the x table and the y table. Now before, we've only dealt with one table, right? Either an x table or a y table. Now we're going to have to do both of them. And you're going to have all the same things we learned about before. You're going to have, for example, x1, right, the initial x, x2. See, let's think about what is x1. Usually we're going to set x1 to be the beginning where the ball, or whatever the projectile is about to, and x2 is where it finally lands, right? Maybe I might find out where x2 is at the middle. I can ask lots of questions. And then we've got v sub x. So now let's talk about, and then we've got initial 1, and then vx2, and we've got a, and then we've got time. So these are our variables. I'll explain that in this diagram in a second. And we have exactly the same things, y1, y2, vy1, vy2, a sub y, a sub x, if you will, and time. Now, in the real world, okay, here on Earth, when we talk about this, the key thing to understand, it says it's moving in two dimensions but accelerating in one dimension. So gravity only works downward, right? We've talked about this before. And when gravity only works downward, the only acceleration that's happening, acceleration due to gravity, is in the y direction. So what is the acceleration in the y direction? It's negative 9.8 meters per second squared. That's always going to be the case. And what is the acceleration in the x direction? It is 0 meters per second. That's key to understand. So as the ball moves across the trajectory towards the hole or whatever they're shooting towards, it's going to not accelerate. It's going to move, right? We know that. You've played golf maybe before. This is the key thing to understanding this. And let's make a really, really important note about time. When you are working these problems, time is the connector, all right? We'll do some problems, but it's the connector. So the time in the x direction and the time in the y direction is always the same number. If the ball is in flight for 22 seconds, then it's going to be in the x direction or the y direction for 22 seconds. It's not going to matter. So if you're trying to connect the x and the y, solve for time. Time. Now, let's talk briefly about the v's here. Oftentimes, you're going to know the velocity of the trajectory, okay? So if I have, okay, if I'm shooting this ball and it's going at 22 meters per second, I have no idea what a good speed is for a golf ball, but let's pretend that it's 22 meters per second. It's going to have, that is 22 degrees that's both going in the x and the y. And let's say our angle is 20 degrees or something like that, okay? So he's shooting at a 20-degree angle, 22 meters per second. I have to use SOHCAHTOA, and really so and ka. I want to use SOHCAHTOA, trig, to find out what the Vx and the Vy initial is, right? If I wanted to find the Vy is the adjacent over the hypotenuse. So that adjacent over the hypotenuse could be, Vy would be cosine of 20 equals Vy over 22, right? And I would solve for that problem, etc. So that's the idea, and then that way you would plug that into the Vy. For Vx, it would be just the sine. So that is the essence of projectile motion. Now, this one, by the way, there's actually like 3 or 4 types of problems. The first type is you shoot on level ground and you land on the same height. So the height, if you will, y1, in this problem, y1 is 0, because if we're going to say, this is 0, he's going to land at the same elevation, so 0. So oftentimes y1 and y2 are 0. x1 and x2 won't be 0, but y1 and y2 would be 0. But let me explain that's like one type of problem when you're on level ground. There are 2 other types. So let's actually call this a type 1 problem. A type 2 problem, you might envision this. You might have a cannon shooting off of a cliff, okay, and it shoots off of a cliff and it hits a ship. This is an ocean, let's say. We have a ship, and it's shooting off of the ship, and then how far is it going to go? You might still have an angle, of 20 degrees or something like that, and this is if you call a type 2 problem. And you'll know the angles, you can figure out the velocity, so when it lands, it's going to go faster. Well, let me say some of this. If you're on level ground, the speed of this is 22 meters per second. When it hits over here, it's going to hit at 22 meters per second. And by the way, we're now making an assumption that there is no drag. There's no air resistance. All right, and we're going to make that assumption for quite a time. And it's usually a pretty good assumption, by the way. So we've got this 20-degree angle, but now if we say, if this is y equals to 0, and say this is y equals to 100 meters, then now we have different y's that we're going to plug into this equation. But the key, guys, is we are going to plug everything into these variables, and then we're going to use our 3 kinematic equations and solve for things. And then you can figure out what you need to do, but you have to solve x and y independently to do this. And there's a third type, let's call it type 3. And actually type 3 is maybe the easiest one, TYP, type 3. In a type 3 problem, it also might be like a cliff. But in this case, what you have is the cannon, or whatever, is shooting horizontally. So here you'll have like y equals to 0, the initial y. It all depends on how you define 0. And let's say this is 100 meters or something. Then you're going to have a y1 and a y2. But in this case, you're not going to have a y vy1 or 2 because it's got no velocity. It's only got a velocity in the x direction. So if this is coming out at 10 meters per second, then the Vx is 10 meters per second. That's it. Vy is initial is 0 because it's not going up. Okay? And then there's a myriad of questions. We might ask how long is it in the air. We might ask at what height does it reach its peak. There's like a million different questions that can be asked, and we're going to solve some of those problems in the next couple of videos. Houston, we don't have a problem.